now we will look at this program. So we will compute 5 factorial, and we will not use printf because writing printf, implementing printf is a lot of work that I didn't want to do in assembler. Okay, well, what we can look at this. What is it that can disturb our nice, pleasant view that we just jump to a function and then return? Well, when we jump to a function, we need to know where we should return. Okay, so I mean that's quite obvious. When we call factorial and get a value here as a parameter to printf, then we clearly need to return here. Okay, so if we call factorial for 1, then the only thing that we do is to return. Okay, but if we call it, it is completely irrelevant if we call ourselves recursively or if we call any other function. It doesn't matter, it just happens to be the same function. There may be a thought that compilers have to deal with something special when they compile recursive functions. That's not the case, at least not C compilers. It's exactly the same as compiling any function. And when we make a call to this function, well, it just happens to be that one that we call, and not much will be different. Or I mean, nothing will be different than calling something else, except where we go. Okay? So what is it that we need to do now? Recall, we save the return address in when we do a call and some instruction, I mean address. What we do, we say address. What we do is to, and we are here at A, we can say. Then we do R31 is A is, okay, we say PC plus 1. In other words, here. I mean, this place is where we want to return to. And also we say PC is the address that we jump to. Okay, so when we come here, R31 has a value, and what else has a value? Well, the parameter must be stored somewhere, and what we do is to store it in the same register as in power. That means the first parameter is stored in R3, the second in R4, etc. And okay, so what should we do? We should these two, I mean, what I'm trying to do is that you should realize that you need to save this somehow. When we return from this call and want to do return, then we need to use the value that we got in R31. But when we call this, we overwrite that R31. So what we need is to save this R31 somewhere. And also we need to save this parameter somewhere. Okay, that's what we have the stack for. So each function that we call, the first one was main. This is just to demonstrate the idea. And then we call factorial for the first time with 5. And then we will call factorial with 4 as parameter, etc. And we use the stack. This is called the stack frame for this function, stack frame for that, etc. I mean, obviously. And so stack frame. Another word is activation record, but that's not so often used. Activation record. Okay, so what should we save there? We clearly in this function need to save R31 somewhere, and we need to save the parameter, because when we return, R3 will have been overwritten. So we should use our own R3. Okay, so we need to save parameters and return value. And then when we return, we read this value in the place where we stored it. Okay, so now we have a need for creating these stack frames. And how to do that is to use a special register. Well, it's not very special, but we just say we use R1 for that. So R1 is used to say where we can save these things. So when we have created this stack frame, we move R1 down in the stack. And then when we return, so R1 will move there, etc. And then when we make a return, we set R1 to the value it was when we came to that function. Okay. You can read this, but I will not say it. It's basically what I said. Okay, so recall R1 is the stack pointer, R31 holds the return address after a call, and R3, R4, etc. hold parameters. Now we say that execution should start, the machine that we had, it starts at address 0. So it starts to set R0 to 0, and then it sets the stack pointer to 1024. Okay, so the program is here, I for instructions, and the stack pointer is just one too much, so it's just one beyond where we can store anything. I mean, this is address 0 and that's address 1023, so the stack pointer is over there. I write stack pointer or R1. Okay, now we see something interesting, namely we have initialized the stack pointer, and then we call main, and then when main returns we call exit. In Java you have probably used this sometimes, exit with a return value, 1 for instance, or 0. Usually on Unix, if we call exit with 0, then it means to the bash or terminal that the program succeeded. Okay. The return value is stored in R3 as well. R3 return value. Okay, since when we make the return value, we don't need the parameter any longer, so that's fine. Okay, but now we will see something interesting. When we call main and get the result from main, that's really like this. In main we get this return 5, for instance. Okay, what will happen? 5 will be stored in R3. Okay, and then so R3 will get whoops, 5. Okay, and then we call exit with R3 set to 5. Okay, I'm not sure you think this is interesting, but what you can do in main, you can call return with a value. I mean, not call, but use return with a value. Or I'm sure you have been told, and it is like this. You either return from main, or you call exit with the value that you want. And these two, you can either write return 5 or exit 5, and they have the same behavior. So why? Well, since this assembler code uses R3 and then calls exit, it will be the same thing as if main called exit with the return value. And this is not a coincidence, because at least on Linux and Mac OS, but I'm sure on most other systems, there is some startup assembler code which sets up the stack pointer, and then we have this. We call main. I mean, that means we do things before coming to main. Okay. And then we call exit. So they look like this. And that's the reason why you can use exit and return as you wish. Okay, I should also comment on the return value from main. If you write like this, say you have bash prompt and you type gcc a.c, and then you want to run this program if gcc didn't complain, then you can write like this, a.out. Okay, why? Well, gcc also returns from main, and if it returns 0, then it means gcc was happy, and then with this logical AND, bash will continue with the next program if the previous was returning 0, otherwise it will stop. Okay, so that's about setting up the program for initial execution. What we will do now is to call main, which happens to be located at instruction 19. So let's go down to 19. It is here. Let's see. Okay, well, we don't want to count them, but it is this instruction. Okay, so what does it do? It starts with creating a stack frame for itself, which means it's this part which creates the stack frame. Save the return address and decrement the stack pointer. It only needs one word. Okay, and then it makes a parameter by storing 5 in register 3, and then it calls factorial at address 4. Okay, so let's go there. That is 0, 1, 2, 3 and 4. This is address 4. And what it does is to start with saving the return address, and then it saves the register, and then it decrements the stack pointer. Okay, and what does it do then? Well, then it checks if it should return because the parameter was 1, and if it is, then it sets the return value to 1. Well, that's quite stupid because it's already 1. We have just checked it, but never mind. And then we increment the stack pointer, so we restore the stack. I mean, we basically remove the stack frame that we don't need any longer, and then we can jump to R31. Okay. Good that we didn't read R31 from the stack frame, since we have destroyed R31, so we can just take it. Okay, for the other cases, what happens then? Then we should do this. So we subtract R3, I mean we subtract 1 from R3 and get the new parameter and call this recursively. And then when we are back here, when we have done this, this will be saved in R3, the value. That we can be sure of. Okay, so what we do is to load the parameter, this one, into R4 and multiply them, and then we use R3 as the destination, since the return value must be put there anyway. And then we need to reload the return address, and we need to increment the stack pointer, and then we can jump to this register. And now we have compute, that should be a 4. And then we have computed this. So where do we return? Well, it depends on where we were in this recursive calls, but eventually we will have return to main, and then we are here, and we don't call printf in this place, and what we do instead is to reload the return address that we saved there and jump there. Okay, so now we are back here and call exit, and exit does not very much. It just stops the machine. In C and other languages, more things happen in exit. For instance, all open files are closed. That means if you have written something to a buffer, I mean, okay, say we saw in the first lecture, we could do like this: fprintf file pointer and something, hello. Okay, this string is printed to a buffer that is accessed using this one. And when this buffer is typically 4 kilobytes. It can be. Okay, and it will put hello there, and when this buffer becomes full, it will print everything to the file. But in this case, I mean, if we assume that we only printed hello, then this will not be full. So we have just written this. Then it will call exit eventually, and everything is that was buffered is dumped to the file if it wasn't before. So exit is not just stop the machine, but it's doing various things. Okay, we will now reflect on, or we can do that at once actually. Oops, we haven't run the program yet. That we need to do. So a.out and factorial, it gets 120 in that register. But what do you think will happen if we change the program slightly to instead compute factorial for 5000? That's not so kind, but what do you think will happen? It will clearly be a disaster, because let's see if we have this. Well, what will happen is that we will call factorial 5000 times, and that will not fit into this, so the stack will eat up everything and it will be chaos. So let's see what happens. Illegal instruction. How come? We will not investigate it, but what has happened is that we have overwritten the program. So it's just garbage here, and the machine.c simulator could not find out what to do. I mean, it was not a valid instruction any longer. Okay. So here we can see where they put the different return, how the stack was used. Okay, so let's go through the rest right now. What will happen if main tries to compute a factorial of 600? Well, it will crash. Is this a problem on real machines? No. Well, it depends. If each function has a huge local variable, then it will be a problem. But usually we avoid that, so we can make highly recursive functions without too much risk of crashing the machine. Okay? And so, summary so far. What's the performance of the machine we just saw? It would be disastrous. That's a bit unfortunate, but it's true. The first reason is that both instructions and I mean, when we fetch an instruction or read or write to memory, then we access the main memory, and that one is really slow. It takes several hundred times the time to make an add instruction to access the memory. So it's disaster. And another problem is that we only execute one instruction at a time. Your phone, I mean any phone which is, say, newer than 10 years old, executes many instructions at the same time. And they do that in a very clever way. They guess where they should execute next. And do that in advance. And usually it works out right. If it doesn't, then they have to throw away some work. But modern CPUs, including in phones, they are really sophisticated. And that's the result of a lot of research. Okay, so one important thing when somebody, okay, I should say that it's easy to create a new idea, a new machine which is faster, but what is relevant to the market is to be able to execute existing programs faster. Otherwise you have to ask somebody to rewrite all their programs, and that's not a very good idea. Okay, and another thing, so computers, modern computers, they are tuned to existing programs, but when we write new programs, we want to know how to exploit the existing machines, and that's what this course is about. Okay, so we could add some more instructions and we can rewrite it to VHDL, and then we can send it away and get a ship back and a very heavy invoice, and then we would basically be done, except that it would be terribly slow. Okay, so this is some kind of I mean, I mentioned the first two. What we can also do is to have multiple processors on the same chip. That's, for instance, when you buy a phone and it is a quad core. It means that it has 4 CPUs on the same chip. And in addition, we can connect different chips through some kind of network and get an even more parallel machine. Okay, but before doing any hardware inventions, we need to understand what it is that takes time. So computer architecture is really free to do anything useful with the billions of transistors. But there are some rules that are really important to follow. New ideas, they must lead to substantial performance improvements. Otherwise, it's not much worth. And the programs, I mean not the programs, but the chip should be easy to make a good C, C++, Fortran, or Java, other languages, compiler for them. And they must be cost effective. If you break these, then there are problems. Okay, binary compatibility, that's really something that you expect. Okay, you don't expect that you can run an app from your phone on your desktop computer, at least not yet. Apple is working on this now that they introduce ARM for both their computers and their mobile devices. Okay, so okay, if you have a Windows program, you cannot usually run it directly on a Mac. But as we have learned, if you have a Windows machine, you can run a Linux program with a special subsystem for Linux, okay, in some special way. But you cannot take a program for power and run it on an x86. And inventing a new computer architecture, in the meaning of the word computer architecture, such as x86 or ARM or power, inventing a new one is really a tough thing to do. It costs astronomical amounts of money and big bets that application developers will follow. For instance, Intel, they wanted to get rid of x86. They made a very expensive attempt with a machine architecture together with Hewlett-Packard called Itanium. Well, after a while it was called Titanic instead. But it required new software, new compilers, new many things, and it didn't work out sufficiently fast. Okay, so what they broke were actually three things. Performance, it was not good enough. Programmability, well, but the compilers were not sufficiently mature for this, and it was not cost effective due to they had no mass market as in x86. And worse for them is that AMD saw the opportunity to create this architecture. It's written in different ways, but x86 64. So they took Intel's, they were already doing this with the x86 for the 32-bit, and then they created a 64-bit version of it, and then Intel was forced to skip this. I mean, it was no longer the focus because AMD, this company, they created a market for 64-bit x86 machines. So the attempt to get rid of x86 failed.